Welcome, everyone. We talk a lot about artificial intelligence, large language models, and these massive data centers powering our digital future. But today we're looking at the unsung hero of the AI boom. We're peeling back the layers to reveal the critical, almost invisible secret behind this absolute explosion in computing power. It's a completely fascinating world of microscopic engineering called advanced packaging.
And I want you to keep this one big question in mind as we go through today's explainer. When Moore's law inevitably hits a physical wall, how exactly does AI keep getting faster and more capable? Like, if we can't simply make transistors infinitely smaller anymore, what's the magical workaround?
Okay, let's dive right into this. For decades, it was just the steady, predictable climb, right? The tech industry relied heavily on Moore's law, that observation that the number of transistors on a microchip doubles roughly every 2 years. That gave us about a 40% boost in performance each generation. But recently, we've hit a massive collision. On one side, AI is driving this explosive demand for incredible compute power. We've got to integrate GPUs with high bandwidth memory, or HBM, at an unprecedented scale. But on the other side, chip miniaturization is literally facing the absolute limits of physics. We simply cannot shrink the silicon much farther. So, advanced packaging has stepped up as the definitive single solution to keep performance growing. Which brings us to Section 1, the breakthrough, from mechanical to chemical. To really understand this leap, we've got to look at the stark contrast between the old way and the new way. Traditional packaging was, well, relatively straightforward. It relied on physical, dry processes. Think of mechanical wire bonding connecting a single chip to its frame. But advanced packaging? That is a total paradigm shift. It moves completely away from those simple mechanical connections and leans heavily on the front end of the wafer fab. We're talking highly complex, wet chemical processes designed for heterogeneous integration, which is basically stitching together completely different types of chips into one massive superchip. And to understand the sheer scale of this leap, we have to talk numbers. Traditional packaging dealt with lines over 10 micrometers wide. Now, we are down to sub-micron levels, less than 2 micrometers. For context, that's roughly a 50th the width of a single human hair. And because the scale is so unfathomably small, the environment has to change dramatically too. We go from your standard class 10,000 cleanroom to a hypersterile class 10 to 100 cleanroom. It requires an unbelievably pristine environment because literally even the most minuscule contamination can ruin the entire structure. Let's actually visualize this. This right here is your classic before picture. Traditional single-chip wire bonding on a substrate. It's a single, isolated silicon die just sitting there on a board with tiny wires looping down to connect it. I mean, it's functional, sure, but the I/O density, the amount of data that can travel in and out at any given moment, is pretty low. It's kind of like having a one-lane country road connecting your house to the rest of the world. Now compare that to the after picture. This is advanced 3D packaging. Notice the extreme density here. Instead of one chip, we've got multiple dies stacked directly on top of each other. Instead of looping wires, we have micro bumps, copper pillars, and multi-layer redistribution lines, or RDLs. This isn't a one-lane road anymore, folks. It is a massive, multi-level superhighway designed specifically to handle the colossal data throughput required by modern AI. Section 2. The blueprint. City planning for microchips. If we think of chips as buildings, a 2.5D IC is a lot like horizontal urban sprawl. You're placing multiple chips side by side on a foundational layer called a silicon interposer. They communicate horizontally across these incredibly tiny microscaled routes. Meanwhile, a 3D IC is like building vertical skyscrapers right in a crowded downtown. You're stacking the chips vertically, one over the other, packing the absolute maximum amount of processing power into the smallest possible physical footprint. But hey, if you build a skyscraper, you need a way to get between the floors quickly, right? Enter the TSV, or Through Silicon Via. These are quite literally the elevators of our 3D chip skyscrapers. They are microscopic tunnels drilled directly through the silicon, creating a lifeline for the absolute shortest possible vertical communication between stacked layers. Without these lightning-fast elevator shafts, vertical stacking just simply wouldn't work. So the crucial point here is that not every application needs the exact same type of city. The industry has actually developed different platform architectures for vastly different use cases. Take the CoWoS family, which stands for Chip on Wafer on Substrate. For mobile devices, you have InfoPop, the industry's first 3D wafer-level fan-out packaging. For top-tier performance, you use CoWoS S. If you need something a bit more cost-effective, there's CoWoS R. And for extreme flexibility, there's CoWoS L. Let's look a little closer at those last three. Here is CoWoS S. This features a full silicon interposer beneath the logic chip and the high bandwidth memory. Because it uses a complete solid layer of silicon to connect everything together, it offers absolutely unmatched speed and density. This specific architecture is the gold standard. It's the top-tier configuration powering the AI chips and supercomputers that are making all the headlines today. But, as you can probably guess, a full silicon interposer is incredibly expensive. That's exactly where CoWoS R comes in. Instead of solid silicon, this version utilizes a fan-out redistribution layer, or RDL, interposer to link the main system on chip with the memory. It's a highly cost-effective way to achieve fantastic performance without the premium price tag of a solid silicon base. And then we have CoWoS L. This architecture is all about ultimate flexibility. It cleverly combines the power delivery benefits of the RDL layer with targeted local silicon interconnects. That gives chip designers the ultimate freedom to mix and match different chips. Again, that's heterogeneous integration in the most efficient way possible. All right, let's move on and see how all this builds toward the absolute cutting edge. This right here is copper-to-copper hybrid bonding. We like to call this the highest hall of advanced packaging. Remember those micro bumps connecting the layers we saw earlier? Well, hybrid bonding discards those bumps entirely. It achieves a completely seamless, direct connection between chips with a pitch of under 10 micrometers. It requires absolute nano-level flatness. You're essentially melding two independent chips into one continuous piece of hardware. It's wild. Which brings us to Section 3, the invisible defense, protecting the nano realm. Now, what's truly fascinating is the hidden chemical challenge behind all of this. Because advanced packaging uses those wet chemical processes on sub-micron lines, filtration requirements just go straight through the roof. Traditional packaging just needed micron-level coarse filtration to catch basic dust. But advanced packaging? It requires nano-level absolute precision. We're talking about filtering out particles that are incredibly small, between under 5 nanometers up to 20 nanometers. A single rogue particle larger than that can short-circuit an entire AI chip worth thousands of dollars. To really put that into perspective, look at the requirement for hybrid bonding. Because the two chips must be perfectly, seamlessly flat to bond correctly, not even a single 10-nanometer particle is allowed on the surface before attachment. None. Zero. It is a mind-boggling level of precision. For context, 10 nanometers is roughly the size of a single protein molecule. So advanced packaging is just as much a miracle of extreme chemical purity and advanced filtration tech as it is a miracle of electronic circuitry. And to maintain this purity, the industry basically relies on 4 critical defensive lines. First, during the creation of the RDL and copper pillars, specialized filters prevent microscopic wire breaks. Second, when drilling those TSV elevators, ultra-pure chemicals are required to prevent void formations deep in the silicon. Third, the microbumping process requires flawless filtration of high-viscosity fluids to stop microbubbles from ruining the solder. And finally, the hybrid bonding process relies on specialized filtration to achieve that completely particle-free, nano-flat surface. These invisible defensive lines are literally the only things standing between a working supercomputer chip and a very, very expensive piece of garbage. So what should you take away from all of this? Well, the next time you marvel at the speed of a new AI model, remember that the true bottleneck is no longer just how many transistors we can cram onto a flat piece of silicon. The next generation of AI won't just depend on the chip itself, but on how flawlessly we can stack them, connect them, and protect them down in the nano realm. It is an ongoing, microscopic battlefield. The real question is, as our compute demands continue to skyrocket, are we ready for the next level of that battle? Thanks for joining me on this explainer. I really hope it gave you a whole new appreciation for the hidden hardware that actually powers our world.